We are in Boston at the Park Plaza Hotel. This is the 33rd Annual Cognitive Science Conference, CogSci 2011. And we are with Rochel Gelman, who's Professor of Psychology at Rutgers and co-director of the Center for Cognitive Science at Rutgers as well.
Just finished.
So give me some sense of you know, how the field has been evolving and where your own work is at this point and how it fits into this overall picture of CogSci.
My own work.
Yeah.
I guess there are two stages in between. I started out as an undergraduate in honors psychology at the University of Toronto in the heyday of behaviorism's end. So I took courses from Endel Tulving in my fourth year, which was the first time he ever taught cognition. I also took learning from Abe Amsel, who was teaching Hollian theory, basically. And it did an honors thesis with Amsel. And Toronto was basically both philosophically an empiricist institution, British, as well as psychologically very much on the Hollian as opposed to Skinnerian side of behaviorism. Good advice led me to go to graduate school on the West Coast. Accidents led me to be working on a linguistic analysis about which I knew nothing, which led me over to the linguistics department to be. And they were so impressed with that, they taught me linguistics when Chomsky had just hit the horizon. In Endel's course, I had read in Helder and Piaget's Growth of the Logical Child, to the adolescence, and I had to give a 2-hour seminar on it. So I spent a very long time. And then Piaget came out in the form of Flavel's book. So I was there as a graduate student, leaving undergraduate as a well-trained or well-socialized member of the tribe. And I started to list all the things, these little motion, or what were called little SGs, little RGs, as mediators, and it didn't make any sense. Everything was falling apart, and then all of a sudden I'm in this environment on the West Coast that is, putting out all these vibes from Boston, Cambridge. And it was just too exciting to not get involved in it. And I got involved in it in two ways. I did both learning and developmental. Doing learning meant I was doing math psych of learning. So this is the extension out of Stanford at the time. So I did a great deal about you learn from one cube, what happens if you do two cubes, and so on. And knowing that field gave me the idea of how to take on the claim that Piagetian tasks couldn't be trained. I succeeded. And I succeeded with 5-year-olds. That led me to the second phase. I continued to always be interested in learning, but there had to be an there had to be a Baconian phase where I had to find the evidence about what could little kids do. Because the view was you couldn't learn anything if you knew nothing about it in a half hour. And that's what led me into studying early number, early cause, early understanding of the difference between animate and inanimate, and actually one of the very early infant studies on number. So, and that's then led to a whole new theoretical perspective. So
we were at the governing board symposium yesterday evening, and it was on the biology of language.
That's right.
Noam Chomsky spoke.
Oh, I loved it.
But as you're saying, you have at one point a Skinnerian behaviorist school of thought, which Chomsky then basically demolishes.
Yeah.
But how have our ideas of where language does come from shifted since those papers in the 59?
There.
And what did you make of his remarks?
Okay, so there really are two big ideas about language. And one is the very detailed, and I thought elegantly done, exposition of Noam Chomsky's. Basically, where does it come from? Well, the mind has mental organs just that are organized for functions. I don't know that he won't use the word function because he's really doing philosophy. But he thinks that way. So he clearly related it to the fact there's a digestive organ or system that it, of course, interacts with air exchange systems and the whatever, food is eaten in the name of the digestive system, basically. And if you don't get any food, it dies. But if you do, you develop habits of eating. And there's actually some flexibility across cultures. But it's got to be food stuff that the system determines has to have certain characteristics. And basically, that's what he's saying is true about language. Language will have to have certain characteristics. The data that are in the environment have to provide the characteristics that can be mapped to the structure of the language organization units in the mind and how they're organized. For me, that's a very important position, but let me put that aside. The alternative is, oh yeah, somehow the mind has structures, but we're not going to tell you what they are. They're going to do two things. Well, actually, we know we have a learning mechanism called association, which takes as its input data under conditions of frequency and proximity. And that's still the dominant alternative. There's something in between. People have come to realize that it's not a passive intake, that there is some tendency to be biased in certain directions. And so yes, language might bias. Something about language. Bias is attention to certain kinds of food in the environment, if you like. But the uptake and the learning about it is then done by a complicated network of associations that get formed in part, in many ways actually, by the data itself. It's not just associations anymore, there also are statistical computations. Now, some people think of statistical computations as being the equivalent of a variant of the association context, confusing a condition of association with the fact that association strengths grow as a function of statistical variables. So it's frequency that leads to association strength, but you can't pull it back out. You don't get the representation. So the other major thing is representational or not.
So do you think that room that we were in last night was packed? Do you think there was one model of the mind that was common to all of those people, or they're just variant? Is it a general purpose computational device? Is it massively modular with all specialized functions that evolved during the Pleistocene?
I think the bias is towards a massively computational device that has some biases to cut nature in a way that we happen to end up cutting nature. Now, it may be because others in the community help the young learner cut the nature that way because there are special kinds of interactions. So, for example, we know kids are much more likely to learn the meaning of a word if there's joint attention to the object that's being labeled.
Right.
And often the kid will ask for the parents' or the adult's attention and say, "What's that?" over and over again, you know? And there's been a lot of progress on the kinds of help the kid is getting. But what seems to still be lost is that the kid is often asking for it, doing the directing, as if there's something they know they should know, but they don't know it. So you do get a kind of split between how much the learner has brought to the situation in the way of what I call skeletal structures, which then outline the relevance and ask, is that relevant?
Do you think that there's enough information about cognitive science, cognition, neuroscience, all those things together, getting into schools so that schools can actually, teachers can actually employ that appropriately to produce, build better learners?
I think there's enough known about what the nature of the data has to look like in schools. Because of the very accident of people working, using as their basic areas, topics in science and math and reading. Now, these were studied primarily as complex cognition problems. What we get out of this is that the material in math and science must be organized around deep, big ideas. So concepts don't stand alone, vocabulary doesn't stand alone. You might use the metaphor of an onion, where it's all put together. Even if you peel the outside, there's still going to be something core on the inside. Or even you build it up that way. Or the goal is to get it shaped in a certain way such that it attracts yet further interest in the same kind of data. In other words, putting it as structure begets structure. So if you don't have any skeletal structure to start, it's hell on wheels, or hows, to explain how we ever learn anything. So I do think there's enough now known about at least how to create a curriculum from pre-K through grade 3 and then build from there on. And in fact, we've just put out a pre-K science curriculum called Preschool Preps, which is to put kids on a learning relevant path for science and math.
This is before kindergarten.
Mm-hmm. That's where all the work went, right? So once we started to know what the kids knew, I foolishly accepted the charge to work on this with the UCLA Child Care Center. It took us a long time. But since we did it, I think others certainly can do it. And some people are doing it. There are some people at Carnegie Mellon who've done rather well with tutoring systems in at least geometry and algebra. But everybody who does this ends up realizing you've got to build organization and the organization has to be around the principles of that domain. So you don't teach geometry by talking about physics. You actually probably can't teach physics without talking about algebra at least. Right? Mechanics really seems to require it, possibly as well calculus. So that as you go forward, you need to have these organized domains pulled forward in terms of potential laws that could be discovered in another field in a simple system that's not, quote, everyday language. But we know quite a bit about this now.
When you talked earlier about your trajectory into all this, even before that, I mean, why that science at all? Why science? I mean, was it parents, a teacher?
No. Actually, originally to do science, we started because nobody was doing it, and it was clear that something was coming down the pike about how we ought to start earlier and get kids learning things about reading. Now, that was not a good idea because it's well known that many kids have trouble discriminating B's and D's and P's and Q's, and the probability that we're going to have more kids labeled, quote, dyslexic was likely to go up. So I thought, well, why don't we do science? It's fun, you know. They know about the difference between animate and inanimate, the insides and the outsides. We knew they knew the difference between a prediction and checking. We knew they knew how to draw and make marks that were kind of like writing. So we started to put that all together. Kids learn to predict, to check. They keep scientists' notebooks by drawing and are telling them, they tell us what to write. They date their work. All of it takes time over the year, but you've got to build it up. You have to have repeated examples. You're going to do plants, you're going to take them through the full cycle, and you can do 2 plants. That's the beginning of the experimental method. All right?
But your own decision to go into this subject area at all?
Oh, in the first place?
Yeah. Was that
arithmetic was the obvious one. Because we knew something about what we might be looking for. So I knew that the kids were spontaneously counting, and the question was, did they realize that was generating a cardinal value with which you do very simple arithmetic? So I started to research that question, early 70s. Then I was just simply on the lookout for other things. I guess the next thing the procedure we developed was a magic show. And all the kids wanted a causal account of how the numbers had changed. Well, these were supposed to be pre-causal kids. Well, they couldn't want an explanation if they didn't assume there was a cause. So we started to find out, do they understand about causality, you know, order, no action at a distance, etc. And yes, they did. And then Liz Spelke was at the University of Pennsylvania, and we accepted the task of writing a piece on the development of social cognition because we were both very puzzled by the Piagetian position that you had to be at various stages about really physics, when social cognition really wasn't about thinking about physics. And so we started to write a think piece that led to thinking about the difference between the laws of the animate and inanimate world. And I asked my son, does a door have a mouth? He was 3. Oh, he thought that was the funniest thing in the world. At night, when I put him to bed, he said, Mommy, could you ask me some more jokes? Tell me some more jokes like that. Then the next day we're in the car and his friends are there, and he turns to me and says, my mother knows how to tell kid jokes. So I just did more of this crossing of ontological categories. They were rolling on the floor. I said, well, gee, we really have to study this one, if it's that conspicuous. And so we got heavily involved in what do kids know about the difference between the conditions of animate, inanimate motion, the difference about the insides and the outsides, and that turned out to be enormous. So you put these all together, and you have what I call a baby math science beginning.
So this magic show, what I was thinking of when you mentioned magic show was that when I did a PBS series some years ago called The Human Quest, we actually shot some footage with Renee Bayarjon.
Yeah, she's a former student of mine,
Right. I was going to say.
Yeah.
So she has that wonderful magic show where very tiny toddlers are obviously baffled to see something vanish off into space.
Yeah, well, these were preschoolers who could talk as young as 2.5, and we really did a full setup. So we showed them everything, and then we had multiple trials where they helped find the plate that would get them a prize. So they always got a prize, so that's what they get distracted with. And then we surreptitiously changed them. So we'd start out with 2 versus 4, and 4 was the winner, but 3 was the loser, or 2 was the loser the other way around. The cans are shuffled and all that. And then unexpectedly, either irrelevant features changed or the numbers changed. And when the numbers changed, you got this. If we took some, where'd they go? What do you mean? Well, was 4, now only 1, 2. And those were the kind of data we were working with. And the advantage of working with the preschoolers is they talk at some point. So you can know if the surprise is about the fact that something's changed or a particular thing has changed. And it was always clear they thought number changed. 2.5-year-olds were able to be trained on 1 versus 2 and then transfer to 3 versus 4. So they were transferring a relationship to a relationship that's only defined on number. And that's what led to the crazy idea of, well, maybe I ought to try it with babies.
How important is neuroscience to the kind of work that you're talking about?
Oh, I think it's fundamental. The work we're doing, there are 2 things. 1, we're nowhere near where I think neuroscience can do a whole lot. It can probably be useful on the clinical side, as we heard yesterday, because if somebody gets a hole in the head and they can't do what a 3-year-old can do, and they can't do it anymore, well, you've been able to do a diagnosis of what the problem is and then what you might do with it. But we're only now getting precise enough, and only, I think, in the number domain, to have what I think we need, which are psychophysical data of the kind that can then say, if you're looking for a needle in the haystack, it has to have these properties. And that's what vision has done. And it was really critical to have those kind of data, and continues to be. It now cycles, it can go back and forth. But it was the behavioral psychophysical data that led people to postulate the number of rods or the number of visual channels there were, and so on. We're nowhere near there. But I think in the long run, what I'm working on are universals. Universal mental structures that anybody raised in a normal environment, that is their environment, will learn about if the environment offers the input.
So, what do you mean by that?
Everybody can count, unless they don't have any money, it seems. I mean, if you only barter, it looks like it's not critical to go beyond 1 for you and 1 for me. But when you want to keep track of whether you're getting a fair deal, you start to move into some way of quantifying it. And that seems to be what history shows. And that usually leads to an explosion of the count list. Everybody knows the difference between the conditions for animate and inanimate objects to move, the various differences in matter, the difference between real and fake eyes. And everybody knows about the difference between plants and other living kinds of organisms. And they're not born knowing the details. So it's a case of prepared skeletal structures that are prepared for learning the kind of knowledge we need to know to interact as humans without school, without formal, organized instruction.
You mentioned early in your career that you got some advice from a mentor. Mm-hmm. Having now worked through a distinguished career yourself, there was a book by Sir Peter Medawar called Advice to a Young Scientist. Mm-hmm. What advice do you give to your students now?
Oh, they've done very well. Well, there's one fundamental advice. Work on a phenomena. I mean, what is science about? Science is telling us what the world is about, world including humans and minds of organisms. And don't get too caught up in the socialization process of, well, there's this task, and maybe that's the reason something didn't work. Ask why you care about that task. So discrimination learning isn't a domain, it's a method. It's a thing we can do, but when do we do it? Or To study attention, you have to ask yourself, what does it mean for a stimulus to be relevant so it is salient? So what's the underlying issue about what is going to grab attention? So it's always, number one, what's the phenomena? Number two, try to always design a study that takes on more than one hypothesis or one system, so that you don't get caught up in saying, oh no, they didn't do it exactly the way I did. Try to replicate, but always pair what you think with what somebody else thinks, or else we won't move forward, because we don't yet have a full theory that would lead us down the road of how do you break it down such that you don't jump to the chemical level to study genetics. If we hadn't done genetics, it was the Watson and Crick model that made the difference as to what kind of chemicals people were going to look at. Going the other way, in the absence of a model, didn't tell us how it might be organized. The other thing is, I don't know, I don't tell them, oh, yes I do. I have one very serious thing. Before you accept a committee responsibility, call me. Irving Goffman did that for me, because they were guaranteed as young, talented women to be asked to be on ridiculous committees. There weren't enough to go around, and nobody was going to pay attention because they were too young. They had nothing to do with whether it was an appropriate one. But then later on, they get on to too many, and so the trick is to teach them to say no.
What about the role of science in society?
Complicated.
The president talking about restoring science to its rightful place in his administration. What is the rightful place?
Well, the question is, what does one mean by that? That's a really complicated question. There are two ways to interpret it. One is to return it to its rightful place is basically to give it back to the academy. I mean, as we were talking yesterday, the people around Galileo and the like were all doing science in the context of really being ministers in churches. And what they created is recognized as modern science, post-Aristotelian science. And the complaint they ran into was you're getting in the way of the public habit of the church being in charge. And that led to the academy being in charge. And early on, the academy just did it to find out. I mean, there's this famous paraphrase of Niels Bohr saying, who was working on how you crack the atom, never will anybody ever find anything useful out of what I'm doing. So there is that funny business of there's accidents of scientific discovery about the world that can be turned into either useful or not useful things for science. It's very hard to know that you're going to do something that you don't know about, you're going to learn something, and also know that it's going to serve society. So that's one side of the problem. From my point of view, there's such a strong anti-intellectual milieu in the country, one could say restore science to its proper place by allowing it to survive and do what it's best at. That's one way of thinking about it. There are some things I think we can help about because we've been, by accident, been studying things like that go into the STEM sciences. We don't know that much about learning to be an engineer or actually mathematics. But we know a fair amount about what it means to learn science. And we do have the problem of living in the 21st century with a totally illiterate population in these dimensions. I can't believe they know the difference between $1 and $3 trillion. They don't know what it means to say science would be happy with the rounding error of the defense budget. So the level of literacy that's required has jumped dramatically. And I guess in that sense, we have a very serious commitment to, once again, transforming what the level of expected knowledge is.
But it's been gathering pace, hasn't it? I mean, I'm thinking if you think back to when James Conant and Vannevar Bush were advising presidents and setting up the National Science Board,
That's
which
right.
became the National Science Foundation. That's only 60 years ago.
I know. It's amazing, the pace. Some of it has to do with the rapid inflow of money, and then we don't have it. So that's a period that we're out of, and things are changing dramatically. Another has to do with a very large example of an early case of immigration with families whose children are not literate for reasons that have to do that they came from countries that didn't provide the institutions. I mean, we've been through it many times, but this time around it's an enormous big challenge because there's so many kids involved and so much heterogeneity. And that's a big problem. That's a toughie.
So how does cognitive science play a role in solving these kind of problems?
Well, the thing we're most interested in is how you go from a number of people, and there were even some symposia on this. What are the learning mechanisms that move you from one condition to another? What are the cultural milieus that are studied by sociologists, anthropologists, that we need to facilitate rapid catch-up? And in some cases we know a lot, in some cases we don't. And it becomes very clear as you get involved, even at the preschool level, we have to be cycling through, trying and seeing why it didn't work. Often it doesn't work because of the kind of pedagogy that has dominated schools for young kids, even all the way through. I mean, it really is required that who's ever doing the teaching know enough to recognize a systematic error as opposed to a random error and be able to use it. And so we have to teach all of that and how to do that in a very large culture. A huge number of people isn't all that easy either, but we have demonstrations. The next question is how can you give away the products as more than demonstrations such they can be used by others? And people, they call what I think that's usually called scale up, but really it is, how can you say, look, we've gone all through this, we did it with everybody, then we put in other people to see if we helped them, they could do it, we know it's doable. So I think we're there in many cases, but it's an enormous challenge to go from here forward. At least we're not ignorant. And most of it's coming from cognitive science, because it happens to be that the subjects we're really concerned about are ones that have dominated the interests of those who do cognitive science. They're mind, learning, action-oriented questions, all of them, always. So it's critical. And they know about technology, they're not afraid of it. They worry about man-machine interaction. AI has moved heavily in that direction.
We've talked before about Francis Bacon and stuff like that. There's a historical component to a lot of these things. If I gave you a time travel token that allowed you to bring to your dinner table anybody from history that you really would love to have a conversation with and ask questions of, who do you think that might be? Do you have anybody spring to mind?
Well, the first name that came to mind was Salva Luria.
Why?
Well, I thought his autobiography was exquisite in explaining where he came from and what it took. But he also was this enormously broadly educated individual who would know a lot about the history of science. And he was known to be a fabulous conversationalist.
Salva Luria, in fact, was a great fan of Jacob Bronowski's,
Yeah.
Because of and was at the Salt for as a fellow, I think, at some point.
So
and
that's
a Nobel laureate, right?
Yeah. Oh, yeah. So that's the first. I've never thought about it. I think if I could, I'd want to talk to Aristotle. Absolutely. I mean, I've read a lot of Aristotle. I even tried to take the kids' explanations and do an Aristotelian analysis of it, and you could only go a little bit. And that convinced me there has been a massive theory change. I mean, this business about smoke going to its natural resting place is just so incredible. And I would really like to know what he would think if he could if he had the data about phenomena that we have. So, and I guess I'd pick, there's a cluster of people who contributed to the notion of observation that all around Galileo's time. Vesuvius, who was working on what the what the heart and blood system really looked like, and that was wrong until he looked. So those are in the history.
Right. Looking forward, what are you optimistic about?
Well, you can ask the question of that I'll see happen in my lifetime, or in the future. Well, from my point of view, it was extraordinarily exciting when I realized that number might be universal. When I saw it in infants, I saw it cross-culturally, and the same model applied everywhere, but it was very simple. I would like to have the right account of that, because then you can start really asking the suitable reductionist question. I guess what I'm looking forward to is when people who study the mind are no longer dualists.
But
Because in many cases, it's here in the brain, right? So, but what's it? Well, it's a thought. And it's as if they don't go together,
So how would you characterize most of the people in the room yesterday? I mean,
smart, talented.
but what model of the mind do they have, you think?
And
Just to go back to that point.
I think there's enough reason to not be optimistic about connectionism or neural nets a la Hebb, to be concerned that an awful lot of time of talent is misdirected. And there are a huge number of people who are endorsing one version or another of a souped-up associationism, or neural nets a la Heb, which was really just an association model. Until it took forever, for example, to get the notion of a homeostat accepted in psychology. People said, what? What does it look like? Because it wasn't an association system, but it is, in fact, a very important regulatory system. So what we need are more of those. And I don't think we have too much of that. We know quite a lot about animals, about feeding, drinking. When they even stare, still people have not gotten to the point where they're sure they can tell you what's going to make you fat. That is what's going to be too much food. And I therefore don't think there are enough people thinking like No, which isn't to say his is the only way to do it, but he's truly thinking about what kind of system of the mind, of the body, could do such a thing as learn language fast.
In some of the conversations I've been having with people about a future possible X Prize for education, neuroeducation, I'm thinking about talking to Clancy Blair, for example, at NYU, and other people who would talk about the importance, and Mary Brabeck as well, about the importance of the neural correlates of engagement. Because if you can figure out what motivates learning.
Well, here's the problem. Engagement differs depending on the extent to which the communicators share knowledge. In the case of education, and so we're having this conversation, we don't know each other very well, but we share a huge amount of knowledge. So you can ask me a question, I have to think about what did you mean, but then I answer it. You can't do that with a 3-year-old. And that's why it's very important to pay attention to what are they bringing to the situation that we offer them and they happily take. Another way of putting it is they have a lot of control over their own learning, which messes the case up because it's no longer the case we're in control. We can't just say, this is wonderful food, eat it. Your mental models, eat it. Any more than we can get kids to eat food they won't eat. And this one's even harder because at least we know what food to put in front of them, what's nutritious. Mm-hmm. So they will engage it. And then say, I want more.
Well, let me ask you again then, is that something you're optimistic about? Do you think we'll get that solved?
I'm optimistic that we're going to at least get really off the ground and know something about why it is that people all over the world can move around and have conversations about what often gets talked about as intuitive or folk knowledge. I really am. I'm worried simply because I don't know of a really good solution about cracking the problem of conceptual change. Because once you go from counting, once you go from cardinality under addition and subtraction, you're into mathematics. And so it's you have to have a notation system as well. By the way, everybody seems to be able to use drawings as representations, and we don't know enough about it, but that's another interesting one. And kids put constraints on what they put on paper.
So what's the next stage in whatever research you're working on at this point?
Well, I'm thinking about just writing a big book because,
okay.
I am approaching 70. I've started at 25. We're both, my husband and I are on sabbatical, and I'm going to take...
Randy Gallistel, of course.
Yeah. And I will take the time to sort what do I want to write up, but I have an idea about
Does it have a title yet?
Well, there's a kind of cute one so far. Language is promiscuous, meaning that language allows us to insert things from other domains, but aren't in those domains. To the extent we can do that, we've been tricked into thinking that everything's in language. So you can insert numbers into a conversation. You can talk about two cats as opposed to black cats. They don't operate the same way. And if you want to say, here are the 6 things you're going to do in that order, you have to say in that order or respectively. There is nothing in language like that. There's no rules that can map to. And there are a bunch of things like that I'm beginning to see are the case. So in a sense, when Chomsky says communication's out there, I've now heard enough, not from Noam, but from others to realize the whole issue of pragmatics dominates the problem of communication, and it too gets inside the language, so that it's probably a mistake to think about rules of politeness as being part of the, quote, formal syntax, because the way that's done varies from culture to culture, really differently. I mean, in Japanese, every other word's an honorific, and English has them, but they're very subtle. So there's another case, and I've begun to realize there are a number of cases, and you end up with different notations.
So
it's that kind of thing.
All right. So thank you for the conversation. So we'll come back. Maybe will you have it finished by next year?
I don't know, because it's going to take a lot of reading, right?
All right. Well,
I don't think this is a common idea.
I look forward to seeing the outcome. Thanks for talking.
Thank you.